Suppose you have a pair of acids or a pair of protons within the same molecule, and you want to compare those two acids or those two potentially acidic protons to figure out which one is the stronger acid. In organic chemistry, the way that we do that is by looking at the conjugate base to figure out the Bronsted acid strength. Assuming that we don't have pKa's, we can use a set of factors and assess the conjugate base itself. Hey, now, why would you do that? Why would you, if you want to know how strong an acid is, take the proton off of it and then look at its base? So we're going to look at the theoretical foundation of this, and then we're going to look at the factors that we would consider, so the practical aspects. So this first part, this first page, is going to be the theory behind it. The reason that we can compare conjugate base stabilities has to do with this, delta G. So remember from general chemistry, delta G is the change in the Gibbs free energy which is the energy that a system has available to do work. Okay, some other ideas about delta G. Actually, let's get to that in a minute. Well, no, we can do that now. So delta G, if the sign of delta G is negative, that refers to a spontaneous reaction. A spontaneous reaction does not need a continual input of energy to keep going. Positive value of delta G is a non-spontaneous reaction, which means that you do need to constantly put in energy if you want that reaction to continue to go. Okay, so we're going to base our arguments on the following ideas. First of all, the more stable a base is, the weaker it is as a base. Okay, so the weaker the base is, the less likely it is to accept a proton. So a weak base or a weaker base is less likely to grab a proton from an acid. So the more stable the base, the weaker it is, the less likely it is to accept a proton. The weaker a base is, the stronger its conjugate acid. So what that means is that if we can assess base stability, we can assess acid strength. Okay, so let me remind you of another, or not another equation, but an equation that you've seen before, and that is this one. Delta G equals negative RT times the natural logarithm of KEQ. What this equation does is it relates delta G to the equilibrium constant. So this could be KEQ, it could be Ka, it's just some kind of K. So let's do the following. We're going to start by plotting G over here. We're going to start with a pair of acids, and let's call them HA1 and HA2. And what we're going to do is allow each of them to dissociate. So let's say that when HA1 dissociates, what we get is H plus and A1 minus, so the conjugate base of HA1. And let's say that when HA2 dissociates, we get also a proton and the conjugate base of HA2, which is A2 minus. Okay, so each of these processes is described by a delta G. So let's say that this quantity of energy we'll call delta G1, and this quantity of energy we'll call delta G2. Now, this argument that I'm presenting to you involves a couple of assumptions. The first assumption is that HA1 and HA2 start out roughly the same in energy. So they are roughly the same in energy. The second assumption that we're going to make is to assume that both of them are weak acids. What that means is that their dissociations are relatively unfavorable. And what we can see is that their conjugate bases are higher in energy. Now, when we look at the products of each of these dissociations, in each of them, there's a proton. So energetically, that's a wash between the two. So what we're really comparing is the energy of A1 minus and the energy of A2 minus. So the first thing we can see is that A2 minus is farther down on the diagram. It is lower in energy than A1 minus. So A2 minus is the more stable of the two conjugate bases. So this is the more stable conjugate base. A1 minus is the less stable conjugate base. And now let's look at these delta G values. Both of them are positive. Okay, so neither one of them is favorable. But the one that's less positive and therefore more favorable is delta G2. It's a smaller positive value of delta G, which makes it, of these two, the more favorable delta G. So a smaller positive value of delta G. Okay, so from the equation up above, delta G equals negative RT times the natural log of KEQ, what we could conclude is the following. A more favorable delta G signifies a larger equilibrium constant. A larger equilibrium constant, in turn, signifies that you have more dissociation or more proton donation, thus a stronger acid. And a stronger acid corresponds to a weaker conjugate base. A weaker conjugate base is a more stable conjugate base. So CB for conjugate base. So what this means is that if we look at structures and we can assess their stabilities using the factors that we're going to talk about in the rest of this packet of notes, if we can assess stabilities of things, we can back into the acid strength of the conjugate acids of the things that we're assessing the stabilities of. So let's look at these factors and we're going to put this into practice. Now, at the beginning of this packet of notes, one of the things that I mentioned to you was that the ideas that we're looking at in this acid-base section, you're also going to end up applying to other reactions that are not necessarily proton transfers. So this is where this really begins. So the ideas that we're going to be talking about over the next few pages, you will see show up in other ways in other places. So first of all, let's talk about the situation where you're comparing two acids, we'll just call them HA, where the protons are attached to elements that are in the same period of the periodic table. If that's the case that you're confronted with, then the factor that you would need to consider would be the electronegativity. All right, so let's look at a set of acids. So we'll look at CH4, ammonia, water, and HF. So notice that each of these elements, carbon, nitrogen, oxygen, and fluorine, they're all in the same period. They're all in period 2. And we know some things about these already. For example, we know that the pKa of ammonia is 36. And we know the pKa of water is 15.7. So with those two numbers, we already know what the trend is across a period. Which is that acid strength gets greater as you go from left to right across the period. So HF in this set is the strongest acid, and CH4 or methane is the weakest acid in this set. Now, does that mean that HF is a strong acid? No, it just means that it's stronger than any of the other acids in this set. Actually, HF itself is a weak acid. Just happens to be the strongest one here. Okay, now our premise, the whole thing that we're basing all these arguments, or most of these arguments on, is that to determine acid strength, if we don't know pKa's, we look at the structures of the conjugate bases, figure out which one is more stable. That will correspond to the weaker base, which corresponds to the stronger conjugate acid. So what we need to do with each of these acids is pull a proton off and draw the structures of their conjugate bases. Then we're going to compare the base structures. Now in this example, we already know the trend. Okay, we know that the acid strength is increasing as you go from left to right. But what we want to be able to do is to rationalize it in case we don't know the pKa numbers. Okay, so take a base, any base, just use B with a lone pair as a generic base, and pull a proton off of each of these by drawing a little mechanism. When you do that, you'll end up with these four structures. So CH3 minus is the conjugate base of methane. The amidion, which we've seen before, NH2 minus, is the conjugate base of ammonia. The conjugate base of water, known to all of you as hydroxide ion. And the conjugate base of HF is the fluoride ion. We can make some assessments here even before we analyze the structures. Because CH4 is the weakest acid, its base, as compared to all these other conjugate bases, is the strongest. And because HF is the strongest acid in our original set, its conjugate base is the weakest of the set of conjugate bases that we just generated. And then we want to be sure to remember that the weakest base in the set is the most stable base. Okay, so why is that the most stable base? That's the question that we want to understand conceptually now. So the other thing that's going on as you go across a period from left to right is that electronegativity, which I'm going to abbreviate again, EN, increases. Okay, so how does this play into these ideas? First, let's define what we mean by electronegativity. The formal definition of electronegativity is the tendency of an atom in a bond to pull the bonding electrons toward itself. So that's the formal definition. But in practice, we can use electronegativity in a broader sense and just think of it as the tendency of an atom to pull any electrons, whether they're bonding electrons or not, toward itself. Of the four elements here, you'll recall that fluorine is the most electronegative. Now, hopefully you remember that because fluorine is the most electronegative element of all of the elements. So certainly it's going to be the most electronegative element in this set. And so what that means is that it holds its electrons most closely to its nucleus. So it holds its electrons closest to its nucleus compared to the other atoms in this period, which in turn means that those electrons experience the positive nuclear charge to the greatest extent. Thus, those electrons are most stabilized by the positive nuclear charge, or their attraction to the positive nuclear charge. So as you go across the period from right to left, the atoms become less electronegative. Therefore, as you go to the left, they're holding their electrons farther and farther away from the nucleus. So those electrons are less and less stable as you go from right to left across a period. Now, an extension of this idea has to do with the hybridization of the atom that the proton is attached to. So if you're comparing two acids where the protons are attached to the same atom, then the factor that you might want to use is hybridization, or one factor you could use. So let's take a look at a set of acids. So what we're going to look at are three what you would call carbon acids, because the protons that are going to be donated in each case are attached to carbon. So we have three structures. Each of them has two carbon atoms. And so we want to figure out which of these is most acidic and which of these is least acidic. So just like we did before, let's just take a base and use it to draw a mechanism to remove a proton from each of these acids. Now I'm removing these protons, but in each of these structures, it doesn't matter which of the protons you remove. You're going to get to the same result. So the first thing is to draw the structures of the conjugate bases. So there's the conjugate base of ethane. Here's the conjugate base of ethylene. And then finally, we have the conjugate base of acetylene. The next thing we want to do is answer this question. For each of these structures, what type of an orbital is holding that lone pair? So using what we know about hybridization, we can determine that in the first example, that lone pair is held in an sp3 orbital. In the second case, the lone pair is in an sp2 orbital because the hybridization of that carbon is sp2. And then finally, in the last case, that lone pair occupies an sp orbital. Let's think back to the pictures that we saw of the hybrid orbitals. So something like this. So sp3, and then sp2 because it has more s character proportionally. That larger lobe is squished down, and then finally, sp has the highest percentage of s character of the three hybrid orbitals that we're considering, and so its larger lobe is going to have more of a spherical look to it, so it's more squished down. So let's put some electrons in these orbitals, allowing us to see that if you're a pair of electrons in an sp orbital, then on average you're going to be held more closely to the nucleus than you would be if you were in an sp2 or an sp3 orbital. So the more s character that an orbital has, the closer to the nucleus, electrons in that orbital are held. In other words, the more s character in an orbital, the more stable electrons in that orbital are. Now this brings up an idea about carbon atoms in general. Now we have an electronegativity value for carbon, that's 2.5. But not all carbon atoms have the same electronegativity. And the reason for that is because of the hybridization of different carbon atoms. So a carbon atom that's sp hybridized, because it's holding electrons closer to its nucleus, is going to have a greater, what we would call, effective electronegativity. So an sp carbon has a greater effective electronegativity than an sp2 carbon or an sp3 carbon. Okay, let's look at another factor. Now this one has to do with cases where you're comparing acids where the protons are attached to elements that are in the same group of the periodic table, so the vertical divisions. In such a case, what you would be looking at would be either the bond strength or, if we're thinking about this from the conjugate base standpoint, the size of the anion. And by anion, that's a term that people use to refer to the conjugate base. Okay, so let's do this using both approaches. We're going to look at the hydrogen halides. So HI, HBr, HCl, and HF. Now previously, I told you that HF was a weak acid, and it still is. It has a pK of 3.1, not a number to memorize. You already know that HCl, HBr, and HI are all strong acids. As such, they're going to have negative pKa values. Now, one table you could consult would give you pKa values of -8, -9, and -10, respectively, for HCl, HBr, and HI. Now, some of this depends on the table that you look at and how the pKa is being measured. These are all always going to be negative numbers. So knowing those pKa's allows us to predict the trend. And the trend is that acidity increases as you go down the group. So HI, because it has the smallest pKa, is the strongest acid in the set, and HF is the weakest. Okay, so we are going to look at a conjugate base stability argument, but before we do that, let's look at a different way of approaching this that it will be very easy for you to apply in problems and so on. So this is a simple but technically incomplete argument. Okay, so technically incomplete. It doesn't have all of the details associated with the full argument, but it's enough to get you to the right answer. So it's not going to mess you up. So let's do the following. Let's look at a set of data for all of these guys that has to do with the bond enthalpy. So the bond enthalpy for each of these, or the delta H, these are all going to be in kilojoules per mole. And so this would be the amount of energy that you need to put in to break each one of these bonds. So for HI, you'd need to put in 299 kilojoules per mole. For HBr, it's 366. For HCl, that value is 431 kilojoules per mole. And finally, for HF, it's 562. Okay, so what's going on here? Well, first of all, as you go down a group, the atomic radius increases. So F is the smallest, Cl is bigger, Br is bigger than that, and I is the biggest of all of them. Okay, so the atomic radius increases. As that's happening, in each of these HX bonds, H is getting farther and farther away from the halogen. So what's also happening with that increase in the atomic radius is that the HX bond length is also increasing. So remember from general chemistry, the longer the bond, the weaker the bond. And so what this is telling us is that the HI bond, which has the smallest bond enthalpy, is the weakest HX bond in this set. Remember, X means halogen. And so it's most easily broken. It requires the smallest amount of energy to break. Thus, HI is the strongest acid in the set, because if that bond is most easily broken, that means its proton is most easily released to a base. Okay, so you can think about it that way. So two things about it. First of all, again, this is simple, and technically it's an incomplete argument, but it does get you to the right answer. But the other thing about this is that it's not addressing the comparison by going through the conjugate base. So let's look at the conjugate base as well. So let's examine this again from a conjugate base standpoint. Okay, so we're going to look at the outliers. But first of all, let's practice our mechanism again. So here's a generic HX and a generic base. And so we're going to pull the proton off of HX, and we're going to get the following conjugate bases. We'll get iodide ion, bromide ion, chloride ion, and fluoride ion. Okay. Now, just like the atomic radius increases as you go down the group, the ionic radius also increases. So the same trend with size we're observing once we've ionized these guys. The ionic radius also increases. Okay, so this brings in an argument relating to the size of the anion, or the conjugate base, and something called polarizability. Let's define polarizability before we move forward. Polarizability, broadly speaking, is how easily a cloud of charge distorts in the presence of an external charge. So let's say how easily a cloud of charge distorts. All right, so let's look at a couple of pictures. So we're going to draw a picture of an iodide ion, which has a negative charge. And we're going to draw a picture of a fluoride ion, which also has a negative charge. And these are drawn actual size. So let's think about this. First of all, each of these guys has a negative charge. So they have the same charge. In the case of the iodide, that charge is more spread out because iodide is larger, so it has a larger surface area. So we would say, in terms of charge per unit surface area, that iodide has a low charge density. And using a similar argument, since the fluoride ion is so much smaller, so it has a smaller surface area, but the same negative charge, the fluoride ion has a high charge density. So the charge on the iodide ion, to push on this a little bit further, is more spread out. Or, in chemistry terms, it's more delocalized. That means that it is more polarizable. So think of it this way. It's squishy, it's easy to distort. So if you think of these by analogy, an iodide ion maybe is like a regular marshmallow, whereas a fluoride ion, because it's small and compact, is more like one of those little marshmallows that comes in those packets of instant cocoa. Okay, so they look like little, I don't know, like little grains or something. So think of that as a fluoride ion. The charge on the fluoride ion is more localized. That makes it less polarizable. Okay, so the fact that the charge is spread out more in the iodide ion contributes more to the stability of the iodide ion as opposed to the fluoride ion, where that charge cannot really be spread out. Okay, now a point that I want to make here is the following. Where am I going to be able to make this? Let's do this right down here. Okay, so we've seen three arguments so far. If you're going across a period, if you're comparing acids that are where the protons are attached to elements in the same period, as you go across a period, you know that electronegativity and size are both changing. But electronegativity is the more dramatic change. So across a period, it's electronegativity that controls, not size, even though both, again, are changing. However, down a group, as it turns out, and as we just saw, even though electronegativity and size are changing, both of those are changing down a group as well, it's size that turns out to be the more important factor, not electronegativity. So keep those things in mind, that although both of those ideas, electronegativity and atomic or ionic size, are changing as you go across a period and down a group, one is more important as you go across a period, that would be electronegativity, and going down a group, the other one turns out to be more important.